Alright, hey guys. So today we're going to be covering the kinematic equations. Sorry if I sound tired. I'm pretty damn tired. So, yeah. Anyways, let's begin. So, an important aspect of um, the kinematic equations is that they can only be used when there's a constant acceleration. So, only can be used there is a constant acceleration, alright? So A has to be constant to be used these equations, right? Most of the time you'll deal with them, but sometimes you won't, and you'll have to try break it down. But here, let's just list all the equations first. These are all provided on the formula sheet, so you'll know how to memorize them. Plus AT. There you go. Remember delta x to reference to change of position, which can also be referred to as displacement or distance. This one's my favorite. B squared equals BO squared plus 2AD. D equals change of x, and then, oh yeah, there's one more. Actually, there should be five. Alright, so I just got interrupted, but I finished doing all the equations here. This one over here, the fifth one, it's much less common, and you will not have to use it as much, but as you can see, these two are almost direct copies of each other, except one uses initial velocity and one uses final velocity, hence the change of symbols. So yeah. Alright, it's a bit hot. So yeah, those are just the basic kinematic equations. At one point, you also have to familiarize yourself with trying to isolate. So for example, if we want to isolate here, we would do B final minus BO at that time, which look at that. That's the same equation for acceleration that we obtain, right? Isn't that crazy? That's because all equations are right hand simple ones at least derived from the kinematics. Okay. So obviously some of them are a bit harder to isolate for. Renownedly, most of the time it's a combination of number three, and number four. These two tend to be a bit tricky to isolate sometimes. So, all right. So let's practice with some practice problems. Yeah. So I'll make these kind of simple so we can use the equations. Let's say a car accelerates um, from rest to 3. So that's a change in velocity for seconds. All right. So A, what is its final velocity? Yes, its final velocity. And B, what's the other factor? Oh yeah, how far did it travel? All right. So first, let's read the question. Okay. So acceleration. So it has a VO of 0 meters per second because it's at rest. B final equals 3 meters per second, and T equals 4 seconds. Alright. So we're trying to find final velocity. So we can use equation number 3. VO squared plus, what was it? 280. Okay. So we can turn this into 0 because 0 squared equals 0. And then you can find acceleration by doing, because look, we have v final squared equals 2AD. Actually, no, we can't even use this one. No, we can't. Oh, what am I doing? I'm trying to find displacement here. Oh, yeah. Sorry, I skipped over question number A. Yeah. So, yeah. Oops. Let's move this to the bottom. So A final equals sec. All right. So that's for A. Now for B, here we go. All right. So divide by 2A. There we go. Those BF squared. Let's do that. Obviously, you can feel free to use any of these equations, really. I mean, preferably you would use this one right here. It's much more simple. It would just be 3 divided by 2 times 4. But we end up with the same thing, really, so it doesn't matter. And divide by time. We know this is 0, so 3 divided by 4. Okay. So we want to put that in a numerical sense. So it'll be 0.75. Oh, just getting my calculator. Oh no. So 3, yeah, 2.75. So now we can plug in since we have every variable. So we have 3 squared times 2, 0.75. So the equals, just plug that into your calculator. 3 squared divided by 2 times 0.75. And you'll get 6. Remember SI units. There we go. Boom. 6 meters. Right? That's good. Okay. So obviously, you can get familiar with all the equations. At the beginning, I obviously do recommend you to just try using like simple plugins, right? So if it's asking you for final velocity. If it's asking you for displacement, use this displacement one, right? You have like 3 available to you. Now later on, obviously you'll start rearranging just like here. I mean, it's a lot easier, takes a lot less time the more you experience with it. So yeah. Let's do another simple question. Then we can up the difficulty a little bit. So this is one of my favorite ones. Ball is thrown. All of these are provided on my textbook. So the ball is thrown straight up. Alright, so straight up with velocity. Uh, 20 meters. Okay. The I'm just gonna assume that's starting velocity. Yeah, because it's been thrown up with 20 meters per second. So how high does that actually go? And then how long? How long? is it in the air for? So that one's basically asking for time. And then this one's just asking for its peak. So really, we can just solve it here. So how does it go? We can assume that this is the Vy because it's straight up. That means there's no horizontal. So we're trying to find the height. We can just use displacement. The question doesn't specify whether it's from rest. So we assume. It's safe to assume. Okay, remember that. So we're trying to find displacement. What's the easiest one we can use? Oh, probably the second one. Equals, what was it? Vf plus Vo divided by 2 times t. So this is in the vertical sense. So I'll cover that later in our vectors episode. I mean, sorry, lesson. But yeah, it's just simple breaking down of vectors and things like that. Go. So V final, the initial, doesn't matter. I mean, we have 20. This equals 0. Actually, well, they're both equal, really. I mean, yeah. Divided by 2, and then t. Oh, we need one without t. Oopsies. So that's a roadblock. Acceleration, we need time. Do we have to find time? How did I solve this problem? V final time. I mean, oh, we do have acceleration. Oh, I'm so stupid, man. Acceleration equals gravity. Ooh, wow. Okay. Okay, rookie mistake there, huh? Remember, acceleration is always there. It's gravity. Okay. So in this case, you could even do this with, I was thinking about doing it without math, but basically just think about, you can estimate gravity to around 10. Okay. So if it's with a velocity of 20 meters per second, gravity brings it down by 10 every second. So it's gonna go, okay, 20, then we have 10, and then we have 0. So it travels 20 1 second, then 10 in another second, and then here is 0. So it travels a total of 30 up, and then a total of 30 down. Okay. So you could do that visually, but obviously we want to do it with the equation. So we would use, well, it doesn't really matter. Here, we use number 3. So V final squared equal VO squared plus 2AD. Okay, so this is Y. Y. Okay, this actually does kind of matter. Which one? I mean, its final velocity is 0. Right. So it would be its VOY. So this just turns into 0. So we're trying to find dy negative VOY squared divided by 2a equals d over y. There you go. That's a weird problem. But then we just do what? What was it? 20 meters. Well, it doesn't really matter right now. It's proper notation. 2 times 10. So dy would equal negative 20 squared divided by 20. What? Squared. 20 meters. Which doesn't. Um. Oh well. Actually, we don't even know the time, so it could make sense. Because in my thing, I was technically, yeah. So always go, yeah. So here, a lesson for everyone. Always go with, mathematical. Don't go with reasoning. Always. Obviously, you'll have to deal with reasoning sometimes in exams. But yeah. So how long is in the air for? This just asking for time. So which one is time? Here we use the first one. V equals VO plus half of AT. I'm pretty sure it's half, no? Oh, it's just AT. Oh, here we go. So T equals unknown. V. So this is all in the y direction. So this equals 0. The problem is that's not specified in this question, but obviously we know that V final is going to be 0 because it lands back, right? Because we are assuming that it has a grounding point, so it's going to turn up and then turn down. So when it lands, it has a velocity of 0. So then we have negative VO, y obviously, divided by A equals T. So negative 20 divided by 10, negative 10, sorry, there we go, equals T equals 2 seconds. Oh, okay, so that makes more sense. If it's only for 2 seconds, yeah, it would only travel 2 meters. I mean 20 meters. Because then it means 1 second up here, 1 second up there. Each one of those would be 20 minus 10. So you get 10 meters up, 10 meters down. So a total of 20 meters. So yeah, and my problem was I was assuming 3 seconds, okay? So here we can just change the questions. I'm gonna flip to the page. Okay. Okay, now we got the question. So let's say here, a rocket, space rocket, starts at rest and travels 500 meters Ooh, no, cover that later. Um, Rocket starts at rest and travels 500 meters, let's say, in 10 seconds. Alright, there we go. So finish setting up the question. Interrupted once again. So rocket starts at rest and travels 500 meters in 10 seconds under constant acceleration. So that just gives us a little hint towards what we can use in this question, which would be the kinematic equations because it's under constant acceleration. So what is the actual acceleration? Um, so it's a rocket. It doesn't actually tell us. Starts at rest. Well, just I don't know. What is the final speed? Hmm. Um, the textbook. No, it doesn't matter. I mean, we get the same thing, so we can just do it here. So A equals VF minus VO over time. So this is quite a simple question. So A just equals simple plug. So we have. Oh no, it isn't. Oopsies. We have to use kinematics. Yeah. Duh. So we have. So let's say what we do have. We have time. We don't have acceleration really. Unless, why would it be asking us what's acceleration? If, mm, but we have distance. So we have VO, we have distance. Wait, we have distance? Yeah, okay. Well, let's just check off. With distance, we have VO, because it starts at rest. So we can cancel the time there. Oh, perfect. We can use this. Oh, perfect. Okay. Let's just copy it then. There we go. Boom. So what is it? 500 meters equals 0 because it starts at rest, right? Yeah. Then we have 1/2 times a times. Actually, no, we should rearrange it. AT squared. So we have 2d equals AT squared. But really, we can just square root it. And then we divide by t. So a equals square root of 2 times 500 times time, which would be 10 seconds. So the acceleration 100 square root of that times 10. No, divide by 10. 2 times 500 square root divided by 10. It would be 3.1 acceleration. 3.16 meters per second squared. If we want to confirm that, we can't really. Well, we could, yeah. I mean, it should be right. Then B, final speed. So this one's actually a bit simpler because we can just VF minus VO. So this one's actually a lot easier because it's just VF divided by T because this turns into 0. So, and then VF, because we're trying to isolate for VF, right? Final speed, final velocity equals acceleration times time, which makes sense because you're canceling out the times because it's meters second squared. So we have 3.16 times 10. So the final equals, well, 31.6 meters per second. Got it. There we go. Okay. Then there's a challenge question here, but that one is to do with um that one is to do with projectile motion, which I'll cover next video for sure. Projectile motion, one dimension, no, two dimensions, and vectors. So we can just do a few more. So let's say, okay, what number are we on? 4. Here, let me just highlight these so they're easier to find. There we go. All right. So let's write down the question. Let's say, okay, this one's good. Pretty real case scenario, really. A train needs to stop and not in 200 meters. In 200 meters with an initial speed of like 30 meters per second. Okay, there we go. So, what acceleration is needed? Remember, acceleration can mean slowing down, like speeding up. Same, but it's not. It does not rely on the sign or the thing. That one's also important. And then, what is the final speed? So this one's similar to the rocket one, but it's more horizontal. So let's read the question. Needs to stop in 200 meters and has initial speed. So it has a distance of 200 meters. And then it has a VO, initial speed of 30 meters per second. So A is asking us for acceleration. Yeah. Unknown. So what will we use? Well, probably the same one we used last time. We have displacement, we have initial speed, we don't have time. Okay. Oh, okay, sorry, I'm eating. Wait, they don't give us time, do they? I'm pretty sure they shouldn't. Yeah, we have VO and D. So it's probably one of the simpler ones. Hmm. Oh, I'm so. Okay. Okay. And now we can just use So the trick there was that I forgot to read the question carefully, but the screen wants to come to a stop, and if it comes to a stop, that means final velocity is zero. So we can just use this one over here, number 3. So v squared equals vo. V squared equals vo plus 2ad. All right, there we go. So let's plug in what we no, sorry, rearrange first. So first, v squared minus vo squared, and then divided by 2d equals a. All right, and then v final 0. So we have, what is it, negative 30 here we go. Okay, by the way, make sure you do the actual math, like algebra properly. Notice how the negative sign is outside the square. So that's not getting squared. So it's only the number that's getting squared, and that keeps negative. And that makes sense, obviously. But yeah, like you'll see later why it makes sense. And then, what's the distance? 200 meters. Okay, so the A will equal 30 squared divided by 400, which equals negative 2.25 meters per second squared. All right, so if we did bring in the negative here and we squared, so negative 30 squared, that would be positive 900, and that would give us a positive acceleration. But that is not possible because remember, with acceleration being a vector, if this wants to stop and slow down, since the velocity is positive 30 meters per second, that means if it wants to slow down, it will need a change in velocity to its opposite, right? And that would be negative. Okay. So obviously there it makes sense. Then final speed, well, we could just use equals vf minus vo. Wait, I know what the final speed is. vf equals 0. We know that. It's from the assumption we made from before, actually. So I think a few of these questions are actually asked the wrong way. I feel like B should be before A. Yeah, it's okay. These were from the start of the year, so let's just do a few more, and then I'll cover what are they called? Oh, key relation graphs. So let's do this one. What number are we on? Number 5. So number 5. Have a ball is dropped. Okay, a ball is dropped from a building. It always helps to diagram these out, by the way. So, and it hits the ground. Hits the ground in 3.2 seconds. Okay, so that's a statement. So the questions are: A, what is the height of the building? And B, what is the speed right before impact or hitting the ground, really? So here we can't assume it's V final to 0, right? So it's a thing. So here we can just draw it out. So this would be h or dy, and then a ball dropped, boom. So that means gravity, but here it seems like we're using real numbers. So we'll use the 9.8, and then t equals 30.2 seconds. So they're asking us for dy, which equals to height, which we don't know, okay? So which one of these will give us that? So we don't have VF. We don't actually. Well, let's look at the other ones. Okay. Mm, wait, was it thrown downwards or was it released? Dropped. Oh, here we go. Dropped. Okay, so that gives us confirmation that BO equals 0 meters per second. Okay, so that makes it a bit easier now because we can use most of them really. We will use. Actually, what am I talking about? I mean, the easiest one obviously is number 4 because we cancel out that gravity and we have time. So we'll use number 4. Boom. There we go. So dy equals bot plus half at squared. Remember this cancels 0 because that's 0. Anything times 0 is 0. So dy equals at squared. Alright. And that's it. So now we plug in. So d of y, or displacement and the height, really, 1/2 of 1.8 times 3.2 squared. So d of y equals 0.5 times 1.8 times Obviously that doesn't make sense, but yeah. Now technically in this case the acceleration would be accelerating it, so yeah, it can't be negative obviously, so it's 50 point, let's just say 2 meters. Yeah, so here we go. So we're trying to find B final. So V final, that's actually quite simple because VF minus VO divided by time. Here you'll notice me, I'm using this simple equation all the time. That's because most of these, you end up like breaking it down, and then with those breakdown variables, you can use even simpler ones. So a lot of time, especially the higher up you get in physics, you'll start breaking down the equations bit by bit, so you can use other easier equations to find even the easier versions of them. So you'll start with like a really tough one, then you find like this variable which can be used in this one, so you can find this variable, and then that variable can be used in this one along with this one to find like this one, and then you have the whole equation already done. So it's a process, right? And you have to be good with algebra. So our acceleration is -9.8 v final minus 0 divided by, oh sorry, we should rearrange first. So this turns into 0. So v final equals AT. So v 9.8 times, how much time was it? 3.2, right? Yes, sir. Or ma'am. There we go. So v final equals. This one does make sense to be negative, right? Because it's going down. 3.2. So negative 31.36 meters per second. There you go. There you go. All right. Now, I think that was good enough practice, right? I mean, just remember, read the question, identify variables, and try to figure out which ones you can use. All right. Now let's move on to key relations. This one is a bit more simpler, really. I'm just going to be talking about the graphs. This is visual. Here we go. So let's say you have an xt graph. All right. So you have a position, which is x, and then time. So as time goes on, the position will get higher, usually like this. Okay. There you go. That's a simple one. Okay. So what can we tell from this graph? This is the important part. So the slope will equal to velocity. Because remember, velocity equals distance divided by time. And the x just equals distance, right? And remember, slope is rise over run. So this would be the rise. This would be the run. So you have x over t, or d over t, which gives you the velocity. So the slope will give you the velocity. And then if it's curved, so let's say the line was curved, curved slope equals acceleration. That's because the actual velocity is changing. So if the velocity is changing, there's an acceleration going on. Okay? And distance times time. And the area doesn't give us anything important. So we can move on to another one. BT graph. There we go, I'm just making it nicer. Okay, so the VT graph. So similar to before, VT. As time gets higher, so the velocity gets higher. This one's kind of like very similar, but you know, slope equals rise over run. So what do you get when you do V over T? Acceleration, right? Change in velocity over change over time equals acceleration. So the slope equals acceleration. But then also, you can always try finding the area of a graph. For example, in the first one, they don't give us anything because it's just, that would be, sorry, displacement times time. So that one is kind of useless to us. But in this case, we have velocity times time. And if we do, so we do V equals D over T, D equals V times T. So in this case, the area of a velocity time graph will give us this area. The area of a velocity times graph will give us the displacement or position, really, right? So the change, and that one's pretty important, right? Because let's say I only have this, right? And I want to find the area of how much distance was traveled at this point, right? So I'll find this area of this triangle right here. So let's say this is my velocity, instantaneous velocity at this instant point in time. So it would be 3.2 seconds, like, I don't know, 20 meters per second, right? And if that times both of them, that'll give me the area, right? And that makes sense because if I was traveling at that speed in seconds and I times it by how many seconds there is, that'll give me the area. The distance traveled. Okay. And then the final one we have is the acceleration times graph. Okay. So this one is also pretty simple. In as of AP Physics 1, acceleration divided by time just simplifies down. So that one is useless to us. But the area is what matters because A times T equals V, because A equals change in V over change in T. So if you want to find velocity, it equals to AT. So then the area, so let's say I was accelerating at 3.5 meters per second squared, and at what, like 8 seconds? I mean, how fast am I traveling? Well, if you times it by time, right, you'll simplify it down, or really you're like trying to find out the velocity. Okay. Because if you're dividing it by time, that means you're getting rid of the time squared, because it's meters per second squared, and then you divide by time, which is seconds. You're getting rid of that extra seconds, which transforms into meters per second, which turns into velocity. Okay. So that's just a simple breakdown if you're trying to understand it that way. So let's note it down. The area equals change in velocity. There we go. So those are all the key relation graphs that you should know. So we have acceleration time, which an area gives you the velocity. There's no slope needed for that one. The velocity times graph, this is one of the most common ones usually. So the slope will give you the acceleration at that point in time, and the area will give you how much distance was traveled at that point in time. Then position time graph, the slope will give you the velocity, and if the slope is actually curved, it means it's accelerating, and the area does not give us anything useful. And then to resume or recap all these kinematic equations, remember, read the question carefully. As you saw in most of these questions, even I, get jumbled up sometimes. I forget to read some key words that tell us about, velocities and things like that. And then also remember, in the vertical sense and horizontal sense, obviously I'll cover that in another video. But yeah, the accelerations will be different. Okay. So that would be it for today's video. Thank you so much for watching, and yeah, good luck.